or afternoon or evening. It's as usual a pleasure to see you all online. We are going to have a very quick introductions and then we will progress to the rest of the course today. I think we are just waiting a few minutes for some more people to log in. As usual, if there is any query, questions that you want to ask, please write it in the chat and we will take care of it in the different sessions at the end of each section of the course. We're going to wait for another minute or so. I'm going to share my screen now. I hope that you can see my presentation.
Yes, we can.
Yes.
Thank you.
That's great. Thank you. So welcome all to this fifth or sixth installments, in fact, even more than that, of our courses. So this is today is on structural resilience of reinforced concrete and masonry buildings. Previous courses, if my, yes, I managed to move it on. So this is the overview of what we have delivered to you so far. I know that many of you have been online for all our offers, and we very much welcome you to this. We will also later today or in the following days send you a questionnaire to just give us some feedback on the quality of what we have delivered so far, but also we would like to hear about what you would like us to engage in. So if you have ideas or if you want to deliver one of those courses yourself, or if you would like to approach somebody that you think would be useful to this community for a talk, then please let us know and please fill in our questionnaire. So today, as here it says, we will deliver this structural resilience part 1, which is reinforced concrete structures and masonry structures. And then towards the end of the month, we will have a system resilience 2, or in which we will look more at the system level of resilience, and now we can recover systems that have been affected by natural hazard by using agent-based modeling and neural network. We already had a first installment of this on the application of Bayesian network to system resilience, so this is quite an interesting counterpart to it. Not often these two methods are used together, but possibly in the near future we will be able to show you how to do this in a sequential manner. So to the meeting today, this is our webpage as usual. You will please go online to the address here to check on our offers. So that you will also find numerous resources as papers and other publications. And you will also find on the Epicenter YouTube website all the recording for all our previous courses. So don't, if you have missed any, you can still catch up on that resource as well. Recently, we have been also delivering face-to-face. So now that we are in a situation that is not anymore affected by COVID, we have started delivering face-to-face capacity buildings exercise, where we are going more in depth on particular aspects of what we have delivered so far online to the whole community. So for clearly small groups, in this case, was a group of colleagues, engineers from Bhutan. But if you're interested in such delivery, also get in touch and we can see what we can achieve. This can be resident at UCL, or we can come and see you wherever you are worldwide. And indeed, these summers, we will also deliver a summer course on structural vulnerability and resilience in collaboration with the Universidad de los Andes in Bogotá in Colombia. And we very much look forward to deliver this course, which goes over 2 weeks, but from the end of June to the beginning of July. And again, if you are interested in being part of this course, register for this course. That can be done both in presence or online, and you can get more information from either the Universidad de los Andes, or you can just contact us directly and we will be able to direct you to the right person for any information and registration. So to the course today, we have 2 sessions, one today and one tomorrow, as usual. Today we will look at some fundamental strategy for retrofitting design, besides a very brief introductions that we are giving. And we will then look at the typical building type, the typical deficiency for a reinforced masonry building type and observed damage, and the typical reinforced concrete building type deficiency and similarly observed damage. Tomorrow, very interestingly, we will have a contribution for Professor Reyes from Universidad de los Andes, Bogotá, on Adobe buildings retrofitting in Colombia. They have done an extensive program of research and actual retrofitting over the past 3 years. And so this is quite interesting. And I think it's very relevant to many of the colleagues that are joining us from various parts of the world. Adobe construction is not materials or method that we have talked much about during our previous courses, but indeed it's a very common construction typology in many parts of Latin America, and not just Latin America, and therefore it's very relevant to our community and audience. We will then continue with retrofitting strategy for reinforced masonry structures and retrofitting strategies for reinforced concrete structures. We will then close with an example of a building that had been retrofitted prior to the earthquake of the Karamansaray in Turkey, occurred in February 2023, and how indeed that particular building survived the earthquakes. And that also is very interesting lessons that can be learned in that respect. And then, of course, question and answer sessions. We look very much forward to hear your answers and to hear your questions, and possibly also to hear some answers from you rather than us providing them. With this, I stop my introduction. And I will just stop sharing for a very brief moment. It would also be nice if some of you can switch on their cameras so that we maybe take a pictures with some real images of people instead of their icons. and get to know you a bit better. Yes, please do so. Thank you again all for joining us. It's so nice to see people in real flesh. I'm now, I see that there is already a comment in the chat. Oh, somebody saying yes to everyone. Okay, great. Yes, I think it's in relation to my previous screen share. So let's see if you can now see my screen again. It should be coming now. Yes?
Yes, we do.
Grazie. Thank you. That's great. Okay, so what am I going to cover in this very brief fundamental? So, yes, sorry, there is a problem with the slides. Just a second. Yep, we should be there now, and hopefully it should be also working. So first of all, why strengthening? Then we will look at what is the structural or seismic assessment process. And to do that, we will refer to the ASCII 4117, not because it's the only process that is available there, but also because it's very well consolidated and, of course, used worldwide. So it's a good reference element. And then we will look at the concept and levels of knowledge. What does that mean when we conduct an assessment? And we will look in great detail at the second part of the assessment process, i.e., how do we move from the assessment of the structures and the understanding of its capacity or of its deficiencies to the productions of fragility functions, and then how do we apply this concept to the actual design or a choice of strategy for strengthening, choice of the strengthening, and then the design itself. So first of all, how do we understand seismic strengthening? So strengthening is the action of reducing the vulnerability of a building to the expected seismic action before the occurrence of a probable earthquake. So the aim of strengthening on existing structures is very much about improving its ability to withstand future earthquakes. Survey, assessment, and analysis are needed to identify the weaknesses and determines the priority for strengthening. And either local or global intervention might be appropriate. And we will see this through the application of the ASCII 4117. The It is worth here to have a definition of vulnerability so that we can relate later the strengthening to the vulnerability, and then why do we make reference to the more general framework of fragility and risk. So vulnerability is defined as the propensity of a building to suffer damage, and in this respect is often confused with fragility. A more specific definition of physical vulnerability defines it as the loss, either economical or physical, expected to be suffered by a given building type due to an environmental action. In this sense, the vulnerability is the summation of the probability of all possible damage states, given a level of excitation, each multiplied by the level of loss associated to it. So a seismic vulnerability functions relates uncertainty loss to a measure of the seismic excitations. And this is depicted in the chart that you can see here, where this is a very qualitative diagram, of course, but we can see that we have an intensity measures on the horizontal axis on a scale of 0 to 10, and the let's say expected damage given, or the probability of damage given that a particular intensity on a scale of 0 to 100%. So we can see in red the strengthened curve, and in blue the unstrengthened curve. And if we consider an intensity measures equal to 8, which for instance in the Mercalli modified intensity scale, so without even getting into the concept of big ground acceleration or the analytical approaches to determine vulnerability, we can see that for a level 8, which is usually considered the level that provides damage, for an unstrengthened structures, possibly a poor masonry structures, we will have that we can achieve as much as 80% of damage, while for the strengthened case, we will achieve a probability of 10% of damage. And this gives you the measure of how the strengthening can actually improve the conditions. And if you can improve the conditions for one building or for one building type, then this approach can be again applied, for instance, at urban level in order to improve the resilience and the response of an entire urban city to a possible earthquake, to a possible future earthquake. This very much gives you the sense of the way in which, even when we are designing a very particular strengthening approach, this only has, it still needs to be related in probabilistic terms to what may occur next. So the seismic assessment can be qualitative versus quantitative. As I said earlier, we can with the graph that I've just shown, that's a very qualitative approach. But we can also do very detailed analysis. So, for instance, the ASCII 4117, as we will see in a moment, covers something as simple as a walk through a site assessment to a detailed quantitative assessment. When we are looking for an assessment, we need to develop a rehabilitation strategy. So why do we want to rehabilitate? To which level do we want to strengthen, for instance? What do we expect that the strengthening will do in terms of reducing the vulnerability? We need to then carry out a seismic analysis and design. And of course, this will identify deficiency, and the deficiency are typically inadequacies in the seismic performance, whether qualitative or quantitative, and we will then, and that will inform the type of strategy and the for the rehabilitation. This might undergo several rounds until we, several loops, because whatever we identified in the design, we might not cover the strategy and the approaches that we intended to achieve. And therefore, it's only when this loop is satisfied that we can then move to the detail of the seismic rehabilitation techniques. The methodology used for the assessment is very important, and we will see how this also relates to the knowledge base. So very quickly, I'm not going to cover, of course, the 500 and extra pages of the 40 of the seismic evaluation and retrofitting of existing building that forms the ASCII 4117. I just want you also to alert to the fact that there will be a new version that is forecast for 23, so this year. Whether it will be ready this year, it's not been promulgated yet. But what I want to alert you to in these graphics that can be then discussed more in detail later is that this is the flow chart of assessment. And as you can see here, there are 3 different tiers. So a tier 1, a tier 2, and a tier 3. The first, but even before starting, you see that there is the needs to define the seismic hazards and the level of seismicity, and there is a need to obtain as-built information. So these are 2 elements of the that constitutes the knowledge, on the basis of which you will then be able to perform either simplified screening procedures, and therefore you will need to define the level of investigation that we were talking about earlier. If the structures does not conforms with a reference building from the standards or a checklist, or it doesn't conform with the compliance of a checklist, which you can find in 4117, but different countries have different checklists, then one can engage in a tier 2 deficiency-based evaluation procedure, which is basically element by element and relates to the single structural element to define whether to identify the weak links. Or one can engage in a more systematic evaluations where a proper structural analysis of the overall model is carried out, considering either a pushover analysis or other type of analysis, but at the system level, or an incremental dynamic analysis or a time history-based analysis. So, but what is important is that even at the tier 3 stage, as you can see, the data collections become a major issue again. And it's to this that I want to refer very briefly, because there is a strong relationship between the way in which the intensity measure is defined, the type of structural analysis that can be carried out, how the risk is quantified, and then how the risk is reduced, and what type of strengthening intervention can be designed. So, for instance, if we are only defining the intensity measures in terms of peak ground accelerations, and we can only have simplified models that provide the capacity in terms of base shear, then we can only determine a ratio of demand to capacity, and this might or might not be in a probabilistic form, but then we will only be able to define interventions that satisfy that lack of capacity in terms of base shear, so in terms of strength. If we are able to define the seismic intensity or the seismic measures in terms of a linear or non-linear spectra, and therefore we are able to correlate the acceleration to the natural period and 2, the displacement given a natural period of the structure, then we are in a position to also define, for instance, a nonlinear pushover analysis. We are then in a, if we have sufficient data and details, we are in a position to look at performance-based criteria in terms of drift, for instance, and we therefore are in a position to determine strengthening intervention, which will also address ductility. Even more so, if we have a more defined, a totally probabilistic definition of the hazards with accelerograms in the nonlinear range, we are in a position to determine a complete life cycle analysis of the structure and therefore understand what is their residual capacity and so on, and look, for instance, at energy dissipation approaches. Therefore, the level of knowledge at which we set ourselves at the beginning and the level of information that we have on the hazard then influence all other aspects of this process. So, framework and a set of guidelines that allows the to pursue this is the GEM Analytical Vulnerability Assessment Guides, which proposes the most suitable and robust method, practical for everyday use for the derivation of analytical seismic fragility curves and vulnerability functions, accounting for regional difference and cultural factors for the classification of building typology and characteristics. The guidelines are designed to enable users to create simplified nonlinear structural model to determine the vulnerability function pertaining to structural response. And the emphasis here is on low and mid-rise building with a load-bearing structure of either reinforced concrete frame or unreinforced masonry constructions. However, the roadmap provided by the GEM guidelines is actually useful for all, for any type of structures. Once you define an index building, then the important components for the response analysis and for the loss repair cost estimation can be identified, whether structural or non-structural. We, depending on the level of knowledge and the resources, different type of models can be determined. Very importantly, the determination of the damage states, and this usually correlates to the determination, to the guidelines in a particular national standard environment. The type of analysis that can be conducted, and this of course has a direct look back on the type of model that will be developed, but you know, several combinations are possible. And while this is the let's say it's the end of the with step 2 run of analysis and outputs of the engineering design parameters represents the end of the seismic structural assessments, then if we want to estimate the losses and mitigate the losses, we need to go through the derivation of fragility curves, vulnerability functions at either all building or component-based building. But quite interestingly, we can use this same approach in the same way, and as I said, for not just for any type of structures, but conceptually for any type of hazards, to then identify the most suitable retrofit mitigations, which can be of different type depending on the type of structure, and then go back to the structural analysis, reperform the structural analysis, reperforms the fragility analysis, and look at the vulnerability analysis, and look at, in that shift of the vulnerability functions that ensure us that we are actually improving the performance of the structure. So the retrofit, at this point, we are in the retrofitting process, and the retrofitting process, according to ASCII 4117, as you can see, matches very closely the process of assessment, in particular in relation to the 2 tiers. but also there are some very important elements. First of all, the selection of the performance objectives, and we will look in a minute what that means. And second, the sorry, this one ended up in the wrong place, the definitions of the building performance level, together with any prior evaluations that we had considered. So in terms of the performance objectives for ASCII 4117, first of all, we look at the different type of seismic hazards, and then we look at the type of performance that we would like to perceive for given level of hazards. So typically, we know that we design building for life safety performance. Some buildings are designed for immediate occupancy, and of course, in some cases, we also want to determine the collapse prevention for an extreme level of hazards. What I would like you to pay attention to is that for existing buildings, and when we define the strengthening performance objective, we used earthquake with a slightly larger occurrence of or return period in the 50 years, and therefore a lesser level of expected magnitude of the hazards. So these reductions in the period, in the hazard return period, corresponds to a lower peak ground acceleration at the sites. And therefore, this means that for an equivalent performance level, we are designing the strengthening to actually be, for that performance level to be met at a lower acceleration value. So we are designing the strengthening for a lower level of hazard than it would be otherwise expected for the equivalent structural design of an equivalent structure. And why we are doing this is because there are many reasons, mainly economical. Another reason is the fact that otherwise, in a new generation of codes, buildings will become immediately superseded if they were expected to meet the same performance objective, for instance, for a higher level of hazards. But also, it's, as I said, mainly an economic reason to make strengthening actually economically viable rather than reconstruction, total reconstruction. And therefore, this has also very substantial implication with respect to the sustainability goals and to the Sendai framework. So as I said earlier, we can choose two different paths again, tier 2 for deficiency-based procedure and tier 3 for the systematic retrofit. When we want to look at the deficiency-based retrofit procedures, there is a very useful document from FEMA that covers the technique for seismic rehabilitation of existing buildings. In the following talk, this would be brought to the front again, and there will be some more details on how it works and how you can use it. I'm now speeding up a bit, but basically here you have different descriptions of different performance objectives. You have a different level of assessment for the 3 different tiers that we have seen in the graph earlier, but also you have different level of performance objective given the reference earthquake and the extreme earthquakes. for different category of buildings. So while for ordinary buildings in category 1 and 2, what we aim to meet is the life safety, structural performance, and non-structural performance. For instance, for building in category 4 or category 4, we require immediate occupancy for structural performance and position retention for non-structural performance, and damage control for structural performance. For category 3 building, schools are, depending again on different nations, sometimes categorized under category 3 or sometimes under category 1 and 2, and in some nations under essentials, especially if they are shelters, under category 4. So what we end up is a matrix of these types, where we have different performance level, where we have different level of earthquakes and return period, and we have therefore different level of target performance for different type of category of buildings. What the fully operational, life safe, and near collapse means, there are some, let's say, qualitative descriptions, and similarly we have some definitions of frequent, occasional, rare, or very rare earthquakes, and you can see here that again we have different level of return periods, but more or less they are within the 475 years, 72 years for the occasional, and so on. Very importantly, when we determine, when we perform pushover analysis or a dynamic analysis, ultimately we create an equivalent backbone curve, and on this backbone curve we will identify drift, which are an identification of what the overall global damage, and they are an identification of the different performance level. So typically, in reference to the ASCII 4117, we have that for the different limit states or performance level, we can also look at different permissible maximum and residual or permanent drift. And we state that in the fully operational level, this should be not more than 0.2%. For immediate occupancy, this should be no greater than 0.5%. For life safety, we are going to 1.5%, and for collapse preventions, we are going to 2.5%. Sorry, it keeps jumping. But what is interesting is that then in the when we are looking at life safety and collapse preventions, we have some permanent drift, and the permanent drift acknowledges the fact that the structures will have been damaged and that we are now taking advantage of the ductility branch of our capacity curves. In the case of life safety, a substantial amount is reabsorbed of that drift when the seismic action is removed. In the case of collapse prevention, we are assumed that the collapse is such that the permissible maximum drift will also coincide with the final permanent drift. But again, that still means that the structure has not collapsed. So in summary, why strengthening? It can be seen that the strengthening would reduce substantially the risk of damage. We have seen the assessment process with ASCII 4117. There are 3 tiers of different complexity and depth with increasing level of time and data and technical expertise. The choice between tier 2 and tier 3 depends on the level by which the building does not comply with the benchmark and the level of knowledge and resources that are available for the assessment. What I refer here in terms of building, of course, can be perceived in terms of an entire typology or an entire urban environment and building stock. The level of knowledge, we have 3 levels of knowledge that can be considered, and this corresponds to the level and depth of the assessment. The same approach can be applied to strengthening. However, the type of strengthening that can be designed and implemented depends on the level of knowledge of the input parameter, i.e. the intensity measure and the information that I have on the structures. The strengthening design process in ASCII 4117 follows the same structures as the assessment process. We have a matrix of performance targets, building category, return period, and type of assessment. And if we want to go to the risk-oriented strengthening, i.e. we want to really understand how the strengthening reduces the risk and therefore how efficient it is in the future, we need to go through the extended GEM approach. And this is for the ones of you that have followed us through the previous presentations, this is fully embedded in the glossy framework for schools and will be mentioned in some of my colleague presentations in the following sessions. And with this, thank you very much. And then unless there are specific questions, I will stop sharing and we can move to the next presentation. I don't see any questions in the chat. So, Ruit, would you like to proceed?
Yes, of course. And they can send the questions in the chat box and we can take them at the end of the session.
Yes, we can take them before the break.
Okay, I will share my presentation now.
We can see your screen.
Yeah, okay. Can you see the first slide?
Yes.
Okay, perfect. Okay, thank you very much, Dina. Let's introduce the general framework of the assessment and strengthening of our buildings. Now, in this presentation, I want to focus on the masonry typologies, mainly unreinforced masonry, and we will see the different masonry typologies and different vulnerability factors that are inherent to masonry structures. And then we will see some damages observed in the past earthquakes, and we will identify thereby the deficiencies. And in the tomorrow session, we will talk about what retrofit techniques have been used, have been exercised to address those deficiencies. So this is the content of my presentation. I will briefly introduce what is masonry, what are the wall level and building level behavior, what are the vulnerability parameters within masonry buildings, and the construction practices. Then we will see the damages observed in the past earthquakes by the masonry buildings, and therefore from that we will identify the common deficiencies that are recurring in masonry constructions, and we will also see some typical examples of good construction practice of masonry buildings. So I'm sure many of you are already familiar with the concept of masonry, how they are built, but I will start with a brief introduction. So masonry, the term is referred to the assemblies of the units and mortar, that is also known as binders. The units could be stone, or earthen materials, for example, rammed earth or adobe, clay bricks, concrete blocks. So, and the binders or the mortar could be mud mortar and lime mortars, which are traditionally used, and cement mortar that are used in modern masonry constructions. So this photograph here shows a typical, one second, I will use my pointer, typical masonry buildings from Nepal or the Himalayan belt, which is rubble stone in mud mortar masonry. So that is traditional or unreinforced masonry. And in contrast, we have modern masonry constructions, for example, reinforced concrete, reinforced masonry, or the confined masonry. But in this presentation, in this course, we will focus mainly on the unreinforced masonry. So we have different combinations of units and binders resulting in different masonry fabrics. For example, the brick and cement mortar fabric, stone, rubble stone in mud mortar fabric, or dry stone masonry. And within the masonry thickness, we can have different bond patterns. For example, here an example of English bond pattern is shown. That is how the workmanship is done through the thickness of the masonry. So at material level, by material level, we mean at the small scale level, for example, 2 units bonded with a mortar joint. We can see several failure modes. For example, the first one is direct tension, where if the units are stronger than the mortar, then the mortar joint is the weak link there. So we have failure across the mortar joint, the interfaces. The next one, B, is the shear loading through. And again, here as well, if the mortar joint is weak, we have shearing failure through the mortar. In the third figure, we have the direct tension in the other direction, where we can see the splitting of units and the mortar joint as well. And we generally encounter combined loading, for example, combined compression, the gravity loading, and then the lateral earthquake loading. In that case, we have mixed mode of failure, for example, splitting of units or shearing through the mortar joint. And under pure compression, we have splitting of both the mortar joint as well as the units. So these are elementary level of failure modes in masonry. Now we move into the wall level. Here in this figure, we have an assemblage of 4 walls, and for the direction of seismic action in this direction, this wall and this wall are under outer plane loading. Outer plane means perpendicular to the wall face, and this one, the long walls, 2 long walls, are subjected to in-plane lateral loading. And this is further elaborated in this figure on your right. We have gravity loading, in-plane loading, and outer-plane loading. And depending on the loading direction, the masonry walls can suffer different types of failure modes, as you can see here, but we will see at individual wall level in the next slides. So for example, the in-plane loading causes different failure modes as shown here. The diagonal shear failure, where the shearing goes through the mortar joints, header joints, and the stretcher joints. Here, there is shear sliding failure, where the mortar is too weak. The whole portion of the masonry can slide. Here we have flexural rocking failure, which is kind of better than these 2 failure modes, because we have rocking behavior. There is no partial or complete collapse here. We have greater displacement capacity of the masonry. And here under combined lateral and gravity loading, we can also see two-way crossing failure, compression failure here. So these different failure modes occur because of the different loading conditions, because of the different size of the piers, the aspect ratio, the height to length ratio, the thickness of the wall, and so on. And these photographs below show some of the experienced damages that are similar to the different failure modes just seen here. These are all in-plane failure modes. On the other hand, when the wall is loaded in out-of-plane direction, the failure modes depend mainly upon the boundary conditions, how they are connected to the rest of the structure. But the cross-wall connections, the wall to horizontally structure connection, and so on. So for example, here, it has poor floor to wall connection at this top level, horizontal level here, and the cross-wall connections are also poor. So the outer plane forces causes the wall to overturn, thereby suffering partial or complete overturning collapse. In the second case here, we have three boundary conditions, three fixed faces here, and the top is free. In this case, there is more strength in the wall than this case, and we can see this type of failure modes here, diagonal bending failure modes here. And in this case, we have restraints on all four sides, and the wall is stronger now than these previous cases. And we can see this type of diagonal bending failures, and it has more lateral resistance than the previous cases. These are some of the examples. Here in the first photo, there is outer plane gable failure because this gable portion is poorly connected to the wall. Here we had better connections at the cross wall level, but we had poor horizontal diaphragm action here in the connection. So it suffered something like this. As you can see, the cross walls are intact there. So these are the general outer plane failure modes that depend on mainly on the restraint conditions, how they are connected to rest of the structure in the building. In masonry structures, the box-like response plays important role in this lateral behavior, because if the walls, the four walls, let's say, in a building, are not properly connected, if they are poorly connected, then individual walls, they behave independently. So they only have the strength of that particular wall, and under outer plane loading, the walls are highly susceptible to overturning collapse. If the walls are properly connected, we have greater strength. We have achieved a box-like response where all the walls act combinedly. However, because of lack of diaphragm actions, the outer plane displacements here at the middle side here, you can see that is more, thus causing the damage concentrated in those areas. So if we have the box, proper box with proper connections of all walls, plus if we add a diaphragm at the top that binds all the walls together and also provides equal displacement to all the walls, then such failure modes of outer plane walls can be restricted. So the seismic response is much more better when we have the box with proper connections plus rigid diaphragm action at the horizontal level. Just some examples of how the walls behave under in-plane and outer plane. For example, this wall is loaded in outer plane under this seismic loading, and this wall is loaded under, this is loaded under outer plane action. This is along the line of the action, so this is in-plane. So the in-plane wall has much higher resistance due to the higher moment of inertia in that direction, while the outer plane is too flexible in that direction. So more deflection, therefore higher susceptibility to damage. This is clarified with the help of the moment of inertia. So if you see here, B is much larger than T. Therefore, this I for in-plane action results in much larger value compared to the I for the wall acting in the outer plane direction. So this I differ significantly for the in-plane and outer plane action. Therefore, if we assume this is a cantilever wall, then the deflection values for the outer plane action, the wall acting in outer plane direction, is much higher than the in-plane direction, therefore higher vulnerability to lateral damage. And instead, if we have all the walls connected properly, resulting in a box, then if we again assume cantilever action, then the moment of inertia will be given by combinedly by all the walls, and we can achieve higher stiffness, therefore very low displacement. This is a numerical example just to see how much they differ in terms of the displacement values. For example, this is same set of walls, poorly connected. Therefore, the outer plane wall, this acts independently. So if we compare the outer plane response of this wall, then we can see using the simple cantilever formulation, we can see the deflection at the top of this outer plane wall is 540 mg/m/E. So these are just modulus of elasticity, mass of wall, the gravitational constant, and those are constant in both cases. But when we have the box-like response, all the walls properly connected, then this wall acts as a single unit. Then we can see the deflection of this system is only 0.92 compared to 540 of the outer plane walls acting independently. So this shows the importance of the box-like action, the importance of connections within the at the cross-wall connections in masonry buildings. Now I will move on to the vulnerability parameters, the most common parameters of the construction practice in masonry buildings that influence the lateral behavior, and that from looking at these different parameters, we can identify what causes deficiencies in masonry buildings. These are 12 parameters listed here, from the material and structural system to height range to seismic design level and so on. So we will see each one by one, but very briefly, and we will see how these the construction practice affect these vulnerability parameters and therefore result in particular deficiencies. For example, about the material and main structural system, we have the structural system of masonry buildings is mostly load bearing. So they work as load bearing walls. But in terms of material, the masonry fabric, we have adobe. Within earthen masonry, we have adobe or rammed earth. You can see these are rammed earth units. And this is quite comparatively new, this cement stabilized soil blocks, which is a kind of adobe, but stabilized with added cement. Under stone masonry, we have rubble stone masonry, traditionally built, dressed stone or semi-dressed stone, the worked masonry, rough faces, and we also have cut stone masonries in recent years because of the availability of stone cutting units. And we have the modern masonry units, the fired clay bricks, and the concrete blocks, which are comparatively bigger in size than the bricks. So if we look at these different typologies of masonry, we can qualitatively identify which one is vulnerable typologies and which one are better typologies in terms of lateral strength. For example, the adobe rammed earth, or this one, the earthen material, earthen units with mud mortar is certainly weaker in lateral performance than the cement binded units, regular units. Okay, so for example, if we look at the size of the units here, the brick masonry here and the concrete blocks here, in terms of the size, the larger concrete blocks provide more shear resistance because there is more area for frictional action there. So larger units are better than the smaller units. So that was the first parameter. Now we move on to the height range. In masonry buildings, we mostly have low-rise masonry buildings extending 1, 2, 3, or 4 stories maximum, most commonly. As the number of stories increases, the vulnerability increases because of higher modes coming into play, the more flexibility of the buildings, and so on. The third parameter is the seismic design level, which is the most important parameter for the lateral resistance of masonry buildings. So the seismic design level means how compliant the building is with the seismic codes in the region, or how well the building is built using traditional craftsmanship, for example. It does not necessarily have to follow the codes. If it is built with proper workmanship, proper craftsmanship, and traditional seismic resisting elements are included in the building, then it can result in a good designed masonry building. For example, therefore, a good seismic design can be achieved by traditional good practices or enforcing seismic design codes. And the seismic design depends on 3 levels of connections. So one is the wall level connections within the wall, how well the wall is built, how good the integrity within the wall is. The second is the cross wall connections, how well the cross walls are connected to each other at the joints. And the third one is global level connections. So we will see each of these. For example, these are indicative of what we mean. So cross wall level connections. Sorry, this is wall level connections, wall integrity, cross wall level connections, and this is global level connections. So these contribute to some extent to box-like behavior, while these bind all the walls together, improve ductility as well, and improve more the box-like response. So we will see each of these one by one. So connections within the wall, for example, traditionally, this rubble stone masonry built, rubble stone masonry walls, they are built with larger units on the 2 faces and filling up the void with smaller units or rubbles or mud. These are traditional practices practiced in the Himalayas. And even in these buildings, traditionally, they have used the bond stones like this or through stones that can help bind the different leaves of masonry together. So that was rubble stone masonry. Now, even in dressed stone masonry, these are traditional practices. For example, using bond units, bond stone or throw stones, binding the 2 leaves together. And in modern masonry, we have different bond patterns. For example, this English bond here, we have alternate layers of stretcher and header bonds, and we have this through the masonry thickness. So proper connection within the wall. And at the cross wall connections, we have these corner stones in stone masonry. We have this corner coin in brick masonry. Even in stone masonry, we have this, and buttresses can also help increase the stiffness or the connections at the cross wall joints. And traditionally, they have also used timber tying elements at the connections, so as to better connect the 2 cross walls together. Now, at the cross wall connections, again, these are some codal recommendations, codal guidance to how to connect the walls together. Now, also at the global connection level, now we have traditionally practiced timber bands, as you can see in this photo here, or reinforced concrete bands in modern masonry. And there are different levels of use of such bands. For example, at different levels, continuously along the vertical, or at lintel level and roof level, or at or for these types of roofs, flexible roofs, there are bands at the roof level, rooftop level as well. So these bands help improve the shear resistance of masonry as well, because they act as they provide more continuous area, so that more friction, and they act as a barrier or a breakage for the continuous diagonal cracks. They improve the integrity also at the wall level and global level, and ultimately they provide better box-like action for the building. So just an indication of what we mean by different level of seismic design. Here we don't see any of those bands or anything here. So this is low design or poor design. Here we have a single lintel band, and this is an example from Nepal, which this building survived with no damage in the 2015 earthquake. So even a simple lintel band can make the building survive major earthquakes. And here we have much more density of level of seismic bands at the sill level, window sill level, intermediate ties here, lintel level band, and then here is roof level band as well. And here the vulnerable gable portion is also eliminated here, replaced with light structure. So the seismic design level increases as we go down in those figures. The fourth parameter is the diaphragm type. We mainly categorize into flexible diaphragm and rigid diaphragm, but there are also semi-rigid type of floor structures. For example, this is a masonry building from Nepal. As you can see here, the roof structure here is well built of timber. The roof elements are tied to the masonry walls with the help of such anchoring or keys, so that they provide not complete box like complete rigid diaphragm action, but they provide at least some level of diaphragm action. And here, just an example of what we mean by flexible and rigid diaphragm. When the diaphragm is flexible, the out of plane walls deform like this, so they are susceptible to damage. While if there is a proper diaphragm action, then all the walls should deform by equal amount, so the displacement is restricted. Therefore, the out of plane failure modes are eliminated. Here, different types of diaphragm actions in masonry buildings. For example, in the first figure here, the diaphragm stiffness is poor. Therefore, the out of plane vulnerability here. There is a proper diaphragm action here, so all the walls are bound to displace together as a single unit. So much better behavior here with the rigid diaphragm action. Here, the structures, the horizontal structures are poorly connected. Therefore, they are taken out, and this wall suffers out of plane overturning here. Here, this at the top, this is properly connected to masonry walls, the horizontal structures. However, at this first floor level, the floor is poorly connected. Therefore, this type of failure mode. And here, there is proper diaphragm action. However, although it has more resistance, it ultimately fails, but it requires a lot of horizontal action for this failure to occur. In terms of irregularity, this picture shows a regular structure, but we might have horizontal or vertical irregularities. Here, for example, the masonry wall ends up here, and there is a replacement by timber. So we have a difference in stiffness in the vertical direction, and this is vertical irregularity. Here we can see an L-shaped building which causes stress concentrations under lateral loading at these areas. So the codes generally suggest us to provide a construction joint, a structural joint, so that we have two separate regular structures. The wall panel length is another parameter which affects the seismic vulnerability. For example, if the wall panels are shorter, then the connections are better. The building has some level of box-like behavior. However, if the wall panels are very long under outer plane action, they tend to behave independently, and they tend to be more flexible because of longer lengths, and the outer plane walls can suffer collapse. The wall openings are also critical in masonry buildings because they control the size of the piers and the spandrels. For example, here the spandrel pier sizes are very small. On the other hand, in this one, where these openings are smaller, we have larger piers, therefore they have more in-plane strength than the smaller piers. And therefore, different codes recommend the position and size of openings. There should be some distance far from the joints. There should be some distance far from the other openings, and the overall opening area, the area of voids in the walls should also be restricted. The foundation usually in masonry buildings is strip type foundation, stepped foundation like this, made of stone masonry or brickwork. And the foundation structure, the response is also affected by the soil type of the site and the depth of the foundations as well. And here you can see a photograph from the earthquake in India. The building suffered damage, and we can see the foundation is too shallow. The seismic pounding risk in masonry buildings is not as common in reinforced concrete buildings, because masonry buildings are low rise. That's one reason, and they are kind of separated. And so basically, the seismic pounding risk increases as the building height increases, and there are different buildings of different heights, so they can suffer hammering at these levels when they respond dynamically differently during lateral action. The seismic retrofitting history in the building also affects its seismic performance. For example, this building is retrofitted throughout this at all wall levels with ferrocement cutting. So the strengthening like this helps to increase the life and increase the safety of the buildings. Structural health condition in traditional buildings, so masonry buildings is standing there since 50 years or 100 years, so the material might have disintegrated. For example, there is a loss of masonry, the mortar here, mud mortar, and this reduces the strength of the walls. Already existing cracks, even minor, they can reduce. They have already lost the bonding, so they have poor cohesion and poor tensile strength. And these are photos of the two ends. One is poor structural health condition, another is newly built good structural health condition. In terms of non-structural elements, we have seen plenty of damage of the under outer plane action of the gables, or even the loosely connected roof coverings, such as this one. The falling of one of these from height can cause severe damage or to humans. So these are also important to look into. So in the newer constructions, so we have realized that the gables, poorly connected gables, are vulnerable because they can overturn on their own. So in the newer constructions, gables are replaced by the light structures. The non-structural elements, their seismic resistance depends on how much weight they have, how well they are connected to the rest of the structures, and so on. So for example, in this building, these large heavy roofs, these structures here, the staircase here, we need to assess how much they weight, so that how much gravity load they provide, and how well they are connected to the rest of the structure. So we will now see some of the past earthquakes and masonry building damage we have observed, and we will try to identify recurring deficiencies and therefore recurring failure patterns. For example, this is from the 2001 Gujarat earthquake. So rubble stone masonry. So here you can see the wall failure, so poor integrity within the walls. Here you can see some portions at the uppermost part of these walls have fallen down, so indicating poor restraint provided by the horizontal structure to the roof. And on the other hand, if you have a proper diaphragm for example, here, the coarse stone masonry building, this one is, and proper diaphragm action can provide box-like behavior. Therefore, there is no out-of-plane collapse of walls. And what we see is the in-plane failure modes, which has much higher resistance than the out-of-plane failure modes. 2005 Kashmir earthquake, similarly, rubble stone masonry here, poor integrity within the wall. There is no box-like behavior, no horizontal diaphragm action. Therefore, out-of-plane failure of the complete wall here. And again, here, when there is an introduction of rigid diaphragm action provided by this RC slab, then we can see the in-plane failure modes, the diagonal shear failure modes. And in here, because of larger openings, here the spandrel and the pier sizes are reduced, very small, so they have poor in-plane strength, so they have failed. 2009 L'Aquila earthquake in Italy. We will see the masonry buildings, which are multi-story, 1 to 3 story, but they seem to have proper floor horizontal structures at floor level. They have proper connection, proper stiffness, but at the roof level, they still lack enough adequate connections and diaphragm actions. So we have this overturning displacement of the gables here. And similarly here, due to the lack of the proper connection and rigidity of the roof, we have seen uppermost floor damage here. In 2011 Bhutan earthquake, similarly here, lack of box-like behavior, lack of diaphragm action, therefore out-of-plane damage. Here again, there is diaphragm, so in-plane failure modes, and here poor cross-wall connection, causing the out-of-plane failure of those upper portions. Again, more examples. Here the poor connection at the corner, so corner failure here. Here the poor integrity within the wall level, so delamination of the outer leaves here, and here as well out-of-plane overturning of this wall, indicating poor connections at the roof level as well as at the floor levels. No diaphragm action. 2015 Nepal earthquake, very similar observations, but for example, the gable failure, the out-of-plane overturning failure, out-of-plane separation cracks here, delamination of the poorly built walls, here also delamination, and here due to better diaphragm action here, there is in-plane failure modes here. And here similarly, no roof, no proper roof diaphragm action, poor connections leading to out-of-plane collapse of this wall here. More examples. This one we already saw. We can see the proper restraints at the two sides, but lack of restraint at the top caused this wall to partially collapse. Here, lack of proper connections of the horizontal and structures and walls, causing the whole face overturning failure in out-of-plane direction. And on the other hand, when we have rigid diaphragms provided by RC slabs here in this building, we have only the in-plane failure modes that are flexural failure or these diagonal shear failures. So by these examples and by looking at the vulnerability parameters for the masonry buildings, we have now clearly identified the recurring failure modes and what are the different weaknesses in the building. So if we talk about now the deficiencies in our masonry structures, we have 3 levels of deficiencies. Wall level deficiencies, which is due to the poor materials, poor units, poor quality mortar, poor workmanship, how well the walls are built, poor connection between the leaves, so no through elements to bind all the leaves together, and large and several openings also reduce the wall level strength, so resulting in inadequate size of piers and spandrels. The second deficiency, the general deficiency, is cross-wall connection level deficiencies. So no use of corner stones, corner cones, or the traditional measures of connecting walls together. Poor workmanship also results in poor cross-wall connections. At the global level, there are poor diaphragm actions, no horizontal bands, poor diaphragm stiffness or connection, so resulting in poor diaphragm action and box-like action. So in terms of engineering judgment, let's say, or engineering computations and so on. So what does these deficiencies mean? We can say, so this wall level deficiencies result in poor lateral strength of walls, easy delamination and debonding of leaves on out of plane action, easier in-plane crack development at the corners of openings when the openings are larger, poor shear resistance, therefore prone to in-plane shear failure. At cross-wall level connections, the deficiencies result in walls acting as individual walls, so independently, no box-like response, easy separation of walls at joints, high out-of-plane vulnerability of complete walls, and there is a chance of also corner failure. When we lack global building measures, for example, the seismic bands and proper connections, we have poor diaphragm action. We have therefore poor box-like response, and we have poor resistance to in-plane diagonal shear failure as well, and poor performance of gables when they are not properly connected with proper rigid bands, rigid slabs, and poor global integrity and poor ductility because the bands provide ductility to masonry. We will see some examples of good construction practice now. For example, on your left, you can see a masonry building supported by timber structures. So for example, there are some timber columns here. There are compression struts here supporting the floor. The roof structure is well built to provide at least semi-rigid type of diaphragm action. And this building has stood for almost 80 years or something, and has suffered 5 different earthquakes, but without any damage. This one is modern cordal practice. As you can see, different bands and even vertical columns providing this strength to the masonry. It looks like confined masonry type. But here in the third picture, you can see timber bands used. There are proper corner stones, large-sized corner stones. So the gable, the vulnerable gable is also replaced with light structure. So this is a kind of blending the modern codes with the traditional best practices. In terms of, so that was mostly about unreinforced masonry. So due to the inherent weaknesses of unreinforced masonry, we started developing the modern masonry, and it has been practiced in several countries across the world, and they are growing. So confined masonry, we have confining ties and columns binding all the masonry, so that improving the integrity of the masonry walls. It also imparts some level of ductility to at the global level. And there is the reinforced masonry, which is mostly used with the help of concrete units, hollow concrete blocks, so that we can put reinforcements and then put grouting through the holes. We use both vertical as well as horizontal reinforcements so that everything is connected, well connected. So we have proper box-like response, and these steel elements also provide a greater ductility to the building. That's the end of my presentation. And I will now, if there are any questions, you can ask quick questions for now, or you can send in the chat box, and we can take them at the very end of this session.
Thank you very much, Rohit, for a comprehensive presentation on the deficiency and efficiencies of masonry structures when they are properly constructed and thought about. Are there any questions, even if you have not put it in the
Yep, if any quick questions
in the chat, we can just answer quick questions.
Or we have the end of our session for Q&A.
Yes.
There is a message in
Good
the
day,
chat.
everybody. Thanks for this webinar. I had a quick question about the UCL June course. Do I need to register in advance? Also, could you provide me with the web page when I can register? Thank you in advance. Okay, thank you very much for this question, Adriana. Can you send me a separate email, please, and we will answer to you. And there is also a question from America. Dina, thanks for this good presentation. Okay, that's personal, so
Okay.
And I think that that's all at the moment. Thank you, Adriana, for your interest in the course. And if anybody else has an interest in it, please email me directly. I will put here my email. Meanwhile, maybe Rafael, because we are running slightly late, it would be good if you can start your presentation.
Yes, Dina, do you want to give like a 3 minutes break?
Yes, shall we have a 3 minutes break for everybody?
Yes, and we can come back at 3:30 in 3 minutes.
That's great. Thanks. Meanwhile, if other people wants to ask questions or anything, please.
Okay, I think that now we are ready to start.
Yes.
Thank you, Dina. Thank you, Rohit, for that presentation as well. We have seen until now some general characteristics of retrofitting, and then Rohit explained us exactly the particularities of unreinforced masonry. So in this third and last session, we are going to see something similar, but for RC building types. So we are going to see some of the deficiencies and the observed damages in previous earthquakes. Just to start, it's very important to understand how RC works as a material. As you all know, concrete is at the end a mixture of cement, water, and aggregate in different proportions. And with this, we can then make an element that is very good in compression, but is not that good in tension. So that's why reinforced concrete also includes the steel, that is a material that is very good in tension. And with this, we can then develop reinforced concrete buildings of different heights and sizes and shapes. With this mixture of reinforced concrete, we can develop beams, columns, walls, slabs. As you all know, it's just to walk in any city and you will see different construction of this type of buildings. It is very easy to generate different shapes and to cover different distances with these elements. So it's one of the materials that is mostly used in cities, but also in rural areas. It's very common to find this type of structural material. Once we understand how the material works, then we can do different type of buildings with this material. And the FEMA 647 divides the structural system in these main three systems. The first one is bare frames, in which we will have only columns and beams. These beams will be connected with a slab with different condition. It could be usually it is a concrete slab. And in here we don't have any type of facade or internal partitions that will affect the behavior of the structure. So therefore, what we will have in here when an earthquake comes and there's some type of acceleration of the ground, what we will have is a deformation that is characteristics of these bare frames. So we will have the shape of the formation of the columns and the beams only, without any impact in the partitions or the facade. This happens when the partitions and the facades are well isolated from the structure, so therefore will not impact on the deformation of the structural elements, or when they are made of some light material that has a very low stiffness, so therefore will not generate any impact in the behavior of the structure. Then we have the RC bare frames with masonry infills. So the advantage of masonry infills is that they are very easy to install and they are commonly used around the world. The main problem with this is that these masonry walls, as Rohit was explaining in the previous session, these walls, if they do not have any type of reinforcement, these are a brittle element. So will generate at the beginning some additional stiffness, will include some additional stiffness to the structure, but then they can affect the building in other ways. It can generate some soft story mechanisms or some short column mechanism, as we're going to see in a few slides. In these cases, it's very important to understand that the behavior of the building will be impacted. We will have a deformation of the walls, of the internal walls, these infill walls, together with the building, with the structural elements, with the columns and beams, and they can therefore get damaged because of the movement of the structure. And the same happens with the facade. Not only for internal walls, the facade can be also attached and will then impact the behavior of the structure. The third big category is RC shear walls, and they subdivided into two categories, which is also very common, and you can see that in almost every code or in almost every building code. The first one is where we have columns and beams, but in addition we have the shear walls. The main task of the columns and beams is to withstand all the gravity loads, while the shear walls are in the structure to withstand the lateral loads and not that much the vertical loads. The second subcategory in these RC shear wall buildings is the ones in which we do not have any type of columns, and the walls will bear all the gravity and all the lateral loads. So we have this differentiation of structures. These are usually stiffer structures than just the bare frames, and we're going to see also in tomorrow's presentation that they have some problems and some advantages as with any type of structural system. So besides the FEMA 647, there are also other type of classifications. I'm going to mention just another one, that is the glossy approach, that is you are following the courses that we have been given in the past weeks and months, we have been presenting all the different glossy tools, and in particular in the glossy taxonomy, the first taxonomical parameter, as Rohit mentioned in the previous presentation, is the main structural system. And specifically for the case of reinforced building, there's a type that is called RC1, which are the simple RC frames, and this is the equivalent to the FEMA 647, the first bare frame typology. So in this case, we have buildings in which they could or they could not, but in the case that they have infills, these infills will have a seismic gap. So the primary elements or the structural elements will be able to deform without interaction with these infill elements that can be located in the interior or in the facade of the building. Or other possibility is that these partitions are light infill walls that will not affect the structural behavior of the building. Remember that the glossy approach and the glossy in general is made for school facilities. So when we go to the second category, the infill frame, in the glossy approach, it is divided into different conditions. The first one is called this RC2, in which we have this infill frame, RC frames, that have these characteristic masonry infills, have some openings, but the openings will not introduce any short column behavior. It can generate, for example, some soft story mechanism, some out of plane behavior, but not the particular short column. And this is because in the glossy approach, this additional structural system that is known as RC3 or RC short column frame is included because in the school buildings, as you can see in here, in this part, it's very common to have this type of windows. They are made architecturally so they can let some air and some light into the classroom, but the students will not get distracted looking outside. And these spaces are also used for lockers for the students. So you can find this type of windows not only in Latin America, as you can see in these pictures, but they are also found in Nepal, in Asia in general, in Africa, and everywhere around the world. So this is a typology that is very common for school facilities, and that's why in the glossy, the World Bank glossy, they decided to divide it into a particular building category. So in this case, what happens is that the frames are not working alone. They are affected by the infill masonry walls. And what happens is that you have a column in here that is restricted until an intermediate height. And therefore, all the displacement will be located only in this short column that is located over here. So the shear stresses will be more than the stresses that the column was designed for. And we will find some failure, and we will see some examples of this type of behavior in previous earthquakes. After that, the next structural system in the glossy approach is the RC4, in which we have an RC combined or dual system. This is the same as the third category of the FEMA 647, in which we have in here a reinforced concrete frame with an additional element that will increase the stiffness of the building. So we can have in here bracing, steel bracing, for example, or a shear wall, as you can see in the picture. Often these elements that will give some additional stiffness are located in the perimeter of the building, but there can also be included in some internal axes. For example, if an RC1 or an RC3 building is retrofitted, one option for the retrofitting is precisely to include this type of shear walls or steel braces, bracing, and therefore the building in the retrofitted condition will change the structural system to an RC4. Finally, the glossy includes a fifth element, that is the RC5. It is a non-engineered RC building in which there are some existing frames, but the structural members are inadequately distributed. So therefore, you will expect a poor seismic performance of these buildings. So now we have understand the different types of a structural system. We go from bare frames. Usually we design the buildings to behave as bare frames. We also saw how the infills will affect the buildings, and after that we saw how these buildings can be included with can be built with some shear walls or any other stiffening element. And finally, we saw that the glossy approach also includes a non-engineered structural system that is also commonly found all around the world and mainly in some rural areas. So before we go to see the different damages that have been registered in previous earthquakes, I want to talk a little bit about the capacity design approach and what is this weak link, how we currently design new buildings. So just to make this comparison with a chain, we have in a building some elements that are brittle and some elements that are ductile. The main problem is that the force that the building should withstand is not known exactly when we are thinking and designing in relation to earthquakes. We can be protected until one level, but maybe a greater earthquake can happen. So we don't know exactly what will happen in the particular region that I am building a new construction. And also the capacities are not known exactly. We can make some safe assumptions of some range of the, for example, the compressive capacity of the concrete and the tension strength of the steel, but this can be also but there is some uncertainty associated with it. So therefore, considering all this, there is a need to tolerate some damage, and in that case, we want to tolerate in the ductile link. So if we go back to the chain will be made of brittle and ductile elements, and if we apply some axial force, we want that the chain failure occur in the ductile element and not in the brittle element. And for this, we need to then ensure that the ductile element maximum strength is lower than the brittle strength. So therefore, we can dissipate energy through the ductility of the building and not through the failure of the brittle elements. In particular, we want that when we are talking about these bare frames structural system, we want that the ductile elements to be the beams and not the columns, because if we give this ductility to the columns, then we can have this strong beam and weak column behavior, and therefore we can have these soft story mechanisms that will generate the collapse of the building. So we want to avoid that type of behavior, and we are going to see in a few slides that this is not what is currently happening in reality and with previous earthquakes. So we want that the plastic hinges that you can see over here that will generate only on the beams, but not in the columns as well. So just to summarize the capacity design criteria, in a building, we can divide the elements into two categories. The first one is the ones that are designated to dissipate energy, and the others are the ones that are designated to remain elastic. So the critical regions of the structure must show this resistance that is higher than the action effects. And of course, this depends on the region that you are designing your building. So it's very important to understand that the fundamentals or the philosophy behind the design, the current and the design nowadays, is to avoid the undesirable failure modes. For example, the shear failure of structural elements. Since the shear failure is a brittle mechanism, we don't want to have that type of failure. We don't want any type of short column, for example, in columns. We don't want any failure in the beam column joints, because if the joint fails, then we will have a failure in all the elements, the surrounding elements. There are a lot of problems with foundations, so we don't expect the yielding of foundations, or in general, the yielding of any other element that is intended to remain elastic. And finally, it is very important to avoid any type of extensive concentration of plastic hinges in any single story. So This is what we plan or what we do while we design a new building. However, this is not usually what happens, and I'm going to show you that in some slides. Before that, we can see in this picture an example of how weak beam is. In here, we have a crack over here and some yielding of the internal rebars, which is exactly what we wanted, and this is what we do not want when the beam is too strong that all the damage will be located in the joint or in the column. So we need to avoid that type of behavior. When we talk about damages in previous earthquakes, the first one that comes in mind is the Turkey and Syria earthquake that recently occurred. I'm going to show you the first 2 minutes of this video to understand precisely why or what happened with all that previous capacity design fundamentals that we just discussed.
Hours after a series of earthquakes and aftershocks on February 6th. First, the bottom floor crumbled. Then, the rest of the building came down on top of it in what's known as a pancake collapse. Thousands of buildings near the epicenter in southern Turkey and northern Syria tumbled straight down in a similar way. The intensity of the earthquakes alone carried the potential for destruction. But it's the pancake collapses that have made this one of the deadliest disasters in the region. Even if there was design, non-acceptable building would have suffered. This doesn't rule out that the buildings was clear of defects. How well buildings protected residents played a significant role in lives saved and lost. Clearly, a lot of these buildings were not up to standard. The death toll continues to climb as many victims are still stuck under the weight of the buildings. So what is it about these buildings that has made this earthquake even more devastating? First, let's look at the larger region that's prone to severe earthquakes because of these two fault lines. They sit along tectonic plates that meet one another and cause friction. When the friction builds up,
Rafael, the audio isn't audible, though.
Turkey has seen major earthquakes along both fault lines.
Sorry, Dina?
The audio isn't audible, so I'm not sure that it works.
Okay, well, no problem with that. Just the idea of the video that you just saw without the audio, no problem. The idea was to show you exactly how these buildings are or what happened in this previous earthquake. We saw a lot of soft story collapses. We saw that the first floor in this type of buildings is usually weaker than the upper stories. So therefore, when any lateral load comes, the failure will be located over here. And this was very common in Turkey, but it's not only common in that region. We can see this type of collapses and this type of behavior around all the world. In particular, it's very important to understand or to correlate this with the slides that we just saw a couple of slides ago with the capacity design. This is exactly what we want to avoid. So we know how this structure fails, but the problem is that they are still failing with what exactly we don't want them to fail. And even in Turkey in 2003, you can see exactly this same type of behavior. So this was a school. You can see here the building before the earthquake, and then you can see here that one story completely collapsed. In particular, this was a soft story mechanism. We can also see a lot of out-of-plane infill failures. You can see all the infill walls rubble over here in outside the building, and you can also see some short column effects over here, and probably the soft story mechanism was triggered by a short column failure in all these axes and maybe in the posterior part of the building as well. And this happened all around the world. You can see here in Nepal also, we can see a lot of short column, this type of damages in which we have these infill walls restraining the movement of the column. but we have some damage located in here. You can see that this effect also in this other picture, and even in this one, in a column that is located in an external axis. A lot of in-plane infill failures, as you can see in here and in these cracks over here. So we can see that the infills are interacting with the structural frame, which is the second typology, and usually buildings are not designed to interact with this, but in the reality, what is happening is that the interaction exists, and this must be considered when we think on retrofitting an existing building. Even in the United States, you can see problems such as material with poor qualities, problems with detailing of structural members. The short column, as I mentioned, happened all around the world. This is an example of Peru in 2001, in which you can see in different buildings the same exact problem of the short column. Also a lot of in-plane infill failures. This is another example in the Dominican Republic. In here, we can see that this building failed completely in this first story. We have a soft story collapsing here, a lot of short columns, as you can see, and also local collapses of some particular parts of the buildings. In Peru, some additional short columns, and one of the most critical problems, the out-of-plane infill failure. So imagine some students or any people that are using this building that try to evacuate over here, and this overloaded canopy is falling out of plane. So it will be a major threat to the human life of the people that are using these buildings. In Chile, we saw a lot of problems with foundations, in which all the buildings end up tilted or even completely collapsed in that sense. Problems with roof failure. In Ecuador, in Muisne earthquake in 2016, we saw the same impacts of soft story, where the hinges were particularly concentrated in one story, and therefore that story collapsed. This is a very iconic case of a building in which two stories were completely collapsed, but the building did not collapse entirely, but of course it was needed to be demolished at the end. And we also saw a lot of problems with foundations, with materials quality, out-of-plane infill failure. You can see in here the same example as in the previous slide, in which the out-of-plane of these infill walls was the problem, and you can see all the rubble over here. So there are a lot of problems that are consistent that we have been seeing in previous earthquakes. So it is very important to understand them. Again, short columns in Peru, in-plane infill failures, out-of-plane infill failures as well. You can see, for example, in here, imagine to have a classroom full of students, and this wall failing out of plane will be a critical problem that should be considered, and it is possible to correct. Another problem is the pounding risk. Rohit also talked about this in the previous presentation, and in RC buildings it's very common to have this type of problems. In school buildings, usually you can find these two buildings just beside the other, and this type of pounding will be a very important problem for the structural safety of the buildings. So just to wrap up, I think that the time is very short now. I just want to briefly introduce what we are going to talk tomorrow about retrofitting, in particular of RC buildings, but tomorrow in the 2-hour session we will talk extensively about retrofitting of different type of buildings. In this simplified scheme, you can see the pushover without any strengthening and the seismic or the design code performance demand. So we can see that without any strengthening, we will have an unsafe behavior, and the strengthening can be done with different objectives in mind. You can increase the stiffness and the strength, as you can see here, and obtain the new pushover curve. You can increase the strength, stiffness, and ductility and have a safer behavior in here, or only rectify local weaknesses and increase ductility. So you will have another type of behavior. And we will discuss more in depth the different strategies for retrofitting that can be used to achieve each one of these cases. According to FEMA 647, there are different categories of deficiencies, such as global strength, stiffness, problems with configuration or load path, diaphragm deficiencies or foundation deficiencies. And there are a lot of rehabilitation measures that can be used, such as, for example, adding new elements, enhance performance of existing elements, improve the connection between components, even reducing the demands by installing some isolation and damping on the buildings, or in some cases, the solution can be to remove selected components. For example, if we are talking with these RC3 or these buildings that have the short column problem, maybe if you remove the infills that are generating the short column, that will help the structure and will avoid early collapses. We are going to talk tomorrow about, in more detail, the FEMA 647. This, as Dina mentioned at the beginning, is a document in which they provide rehabilitation techniques by different model of building types, in which they have different materials and different structural systems. And for each one of these, they provide a description, the seismic response and characteristics, and the common deficiencies, and the rehabilitation techniques with some detailed descriptions and some references. And also, in the framework of the GLOSSY project, there are some vulnerability reduction solutions for different type of taxonomies, building types, and these are specifically designed or identified for school infrastructure and for school buildings. So this is a lot of material that is available in the literature that it is possible to access, and we are going to discuss that in detail tomorrow. So today we covered the fundamentals or the strategy for retrofitting design. In here we talk about the ACC 4117, that is one of the most recent and most widely accepted codes. And we also talk about the building types, deficiencies, and damages in unreinforced masonry and reinforced concrete. So tomorrow we will start with a presentation on earthen buildings, particular adobe buildings in Colombia. For this, Professor Juan Carlos Reyes is going to show us an example of a project that was done in Universidad de los Andes, in which they established different retrofitting alternatives. And then we will talk about more generic retrofitting strategies for unreinforced masonry and for reinforced concrete. And finally, we will see some example of a resilient building that was previously retrofitted that had a very good behavior in the latest Turkey earthquake. So thank you very much. This is all from my side. I don't know if there are any questions, or if you want Dina to finish with some conclusion.
So are any questions there? First of all, please feel free to open your mic and just fire off. As you can clearly see from the presentations today, this is only half of the story, because we are only looked at the deficiencies today, and we very much look forward to meet you all again tomorrow to discuss strengthening. Hopefully some of you will have had also experience of actually assessing buildings and possibly design also strengthening enforcement and so on. So it would be very great to hear from you, and how do you go about it? How do you assess a building, and what are the typical strengthening provisions that you have used in the past, or that you intend to use for the particular deficiencies? If there are no questions, then we look forward to see you tomorrow. There is something, problem? Okay. Problem of joint flexibility in this case, how can resolve this? Asia, can you please explain a little bit better? I can see you are online and with your camera on. Would you mind to expand a little bit on what you mean by this question? What you're specifically referring to?
Major buildings have a difference. The tall buildings or small buildings have a seismic joint. How are the performance or the impact of this joint flexibility to compute or observe damage in this structure?
Sorry, so you have a seismic joint in a small
Yes.
building? And
Yes.
this is between two parts of the same building?
Two parts, yes.
Yes. And
How?
What is
when
this?
you have when you have a different damage in this structure, how can you resolve this for retrofitting?
So typically, well, first of all, it depends on how this seismic joint has been designed and what is the structural type. Is a concrete structure? Is it a masonry structure? What type of structure it is? Is it a steel structure?
Steel, yes.
Steel?
Yes.
Yes, so it's a steel frame with infill?
I have not information of the different characteristic of the buildings.
What is the type of cladding? So typically you would do an elastic analysis.
Yes.
Yes, you would have done an elastic analysis. You would have determined a drift that the structures undergo with the elastic analysis. Possibly, if you are designed for life safety, you would have also done a pushover analysis or a post-elastic analysis. Pushover. So you should have been able to determine the equivalent drift that and the permanent drift that you expect after for that level of seismic action.
Yes.
At that point, the seismic joint should be designed to be larger than the maximum and permanent drift that you have at life safety level.
Okay.
If the seismic joint then fails for some reason, it means that was not properly designed to accommodate that displacement.
Okay.
And then there might be some localized damage of the two parts of the structures due to pounding.
Okay.
And if there is that type of damage, then you need to reassess the structures and check what is the state of the, perimetral element and possibly fix some of them, and then find a way of either increasing the seismic joint that you have or make the structure stiffer so that you will have less deflection in a future earthquake of the same magnitude.
Okay, thank you. Okay.
Now, without seeing the structures in detail, it's difficult to give more precise detail, but that should be the approach that you follow. Then there is another question for RC structures. Is there a detailed vulnerability parameters list? Rafa, I leave it to you to answer this.
Yes, indeed, there is in the framework of the GLOSSY project. As Rod mentioned, there are different vulnerability parameters for unreinforced masonry. There is the equivalent list for RC, and all the information can be found in the GLOSSY webpage. We also give a course of that previously that is available in YouTube if you are interested in knowing more details of that. And beside this GLOSSY, as I mentioned in the FEMA 647, there's also a lot of information of generic deficiencies of this type of buildings, where you can see the short column, the soft story, and different deficiencies that can be analyzed. So to answer your question, yes, there is, and there's a lot of literature on that relation that if you are interested in, you can just send us an email and we can redirect you to the particular web pages and sources of this information.
Yes, so Asana very kindly has already pasted in the chat the glossy web page. I'm not sure whether you were referring to specific vulnerability parameters, or you also include, this is for Kevin Aranja asking this question. So were you referring to specifically the vulnerability parameters list, or were you referring to general structural deficiencies? Kevin, I see that you are muted, sorry. You're still muted.
Yeah, okay, let me unmute.
Yes,
Thank
now
you.
we can hear you. Thank you.
Yes, I'm looking at this in the example for the masonry structures. We have the list like main structural system, the height range, the seismic level, design level, etc., and the different types, etc.
Yes, they are the same. They are the same set of parameters, but you can find them listed in the glossy website, and you can also look at the previous lectures that previous short course that we gave on the glossy approach, which you can find on Epicenter YouTube. Again, possibly Asana, if you are quick-handed,
Yes,
then you can paste, or Rafa, you can paste the website or for that in the chat. Or Kevin, just send us an email and we will send you the details. There is another question. So the seismic gaps were mentioned to prevent masonry infill restraining column deformation, or yes, the interaction basically between infill and columns, but the masonry needs to be restrained against out of plane forces. What sort of details are used? Rohit, would you like to answer this? I don't see Rohit online. I don't know if something has happened to his
Maybe
connection.
he disconnected, but
Sorry,
I can.
Sorry, I'm here.
Yes.
Rafa, can you?
Yes, Rohit. I think that you were mentioning when I talk about these RC buildings and the masonry infill walls that are used as partitions. In this case, the partition should be separated, but in new buildings, this type of partition should be reinforced by themselves. So it can be done using, for example, confined masonry, in which you can include particular columns in the middle, for example, of the column to avoid this out-of-plane behavior. Or you can use reinforced concrete, reinforced masonry units in which you have these vertical holes, and in there you can add some retrofitted inside, so you will avoid that out-of-plane forces. That's for new buildings. For existing buildings, there are two solutions. The first one is to replace the existing infill with one of these technology, and the second is to add some type of element that could be, for example, a steel plate that can be included to avoid that out-of-plane behavior. And in particular, even though we are talking of different type of masonry, but tomorrow Professor Juan Carlos Reyes will explain some of these alternatives for Adobe, but that can be extrapolated for the type of masonry units. But yes, my answer in general is that new buildings can be included from the beginning. The infills can be made to withstand out-of-plane forces, and for existing ones, there are some retrofitting alternatives that can be also used. Thank you for the question, Cody.
Okay, are there any other questions? If they are not for the time being, then we look forward to meeting you all again and more tomorrow, and to continue this conversation. Thank you very much for listening and participating.
Thank you.
Goodbye, everybody, and have a good rest of the day or evening or night. Bye-bye.
Thank you very much
You're
for all
welcome.
the attendees, and see you tomorrow.